Good day. So this is for the introduction for the design and analysis of structural steel members, which are flexural members. So flexural members are slender members that deform primarily by bending moments caused by concentrated couples or transverse forces. In modern construction, so these members may be joists, beams, girders, spandrels, lintels, and other specially named elements. If we are to proceed on our NSCP 2015, that is on page 5-64 of chapter 5, structural steel. Then if we are to proceed on section 506.2. So doubly symmetric compact eye-shaped members and channels bent about their major axis. So if you say eye-shaped members, that includes our W section or sections, or the wide flanges. So this section applies to doubly symmetric eye-shaped members and channels bent about their major axis having compact webs and compact flanges as defined in section 502.4. So the nominal flexural strength M sub n shall be the lower value according to the limit states of yielding, that is plastic moment and lateral torsional buckling. So our nominal moment M sub n is equal to M sub p is equal to Fy multiplied by the Z sub x, wherein our Fy is the specified minimum yield stress of the type of steel being used in megapascals, and the value of Z sub x, that is the plastic section modulus about the x-axis. Now, if you are to recall from our strength of materials, how do we compute for bending moments or bending stress? The bending stress F sub b is equal to the MC over I. Wherein this is the value of C over I, or this term S is our section modulus. The section modulus, the I divided by C, we can have it as S. So the equivalent of our bending stress is equal to the moment divided by our section modulus. But here in steel design, we are not using the section modulus. That is for the elastic section modulus. We are using the plastic section modulus. And we are to use F sub y, the specified minimum yield stress of the type of steel. So from our equation, we have F sub y should be equal to the nominal moment capacity of the section. So instead of section modulus for the elastic behavior, we are using the plastic section modulus Z. With respect to its major axis, Z sub x. So if you are to compute for that nominal moment or the plastic moment, that is equal to the Fy multiplied by the Z sub x. Okay. So here in steel design for flexural members, we have 3 zones. So it depends on the value of our the L sub b. So basically we have L sub b is defined as the unbraced length of our flexural member. Okay, so we have, if L sub b is less than L sub p, that will be our zone 1. If L sub p is less than L sub b and less than or equal to L sub r, that will be our zone 2. And for the last zone, this is if the unbraced length is greater than L sub r, that will be zone number 3. Now let us discuss these 3 zones in terms of the diagram. Okay, we have here, so this is zone 1. That is plastic behavior or full plastic moment. Then we have zone 2, an elastic lateral torsional buckling, that is for zone 2. Then with elastic lateral torsional buckling, that will be zone 3. Then what are the useful equations for these 3 zones? Again, if our section, if our sections will have compact flange, so these are the conditions. The section should have a compact flange. Okay, and we have compact web. Alright, so that is, again, so if we have a section with a compact flange and compact web, that is section 506.2, okay, of our NSCP. So here's the summary, okay, of the useful equations. So based on the length or the unbraced length of the flexural member. So if the unbraced length is less than or equal to L sub B, okay, again, that is our zone 1, a plastic behavior. So if the unbraced length L sub B of the compression flange of a compact section does not exceed L sub P. So how do we compute for the L sub P? Okay, this is our equation. Then for zone 2, if we have L sub B is less than L sub B and less than or equal to L sub R, so this is how we compute for the nominal moment capacity, or the M sub N. And here are the factors. We have the C sub P, the value of L sub R, and the value of R sub TS squared. So we have additional useful equations. So in defense of the type of sections for doubly symmetric I shapes with rectangular flanges, and RTS may be accurately and conservatively as radius of gyration of compression flange plus 1 over 6 of the web. So we have this equation. So it depends on our section. Okay, that is for the case of L sub P is less than the unbraced length of the flexural member and less than or equal to L sub R. And for the third case, we have L sub P, or that is the zone 3. Okay, we have the design of the beams for elastic buckling. So this is how we compute for the nominal moment capacity. Okay, and this is the equation of F sub CR. Okay, so this is the summary of the 3 zones, and it's a useful equation for sections with compact flange and compact web. Okay, now how do we determine, or how do we check if a section is compact? So for us to determine if the section is compact, so we may proceed to our reference. Still, NSCP 2015, page 5-44 and 5-45. If we are to use I-shaped sections, that is that includes RW sections, or the wide flange sections. That will be case 1, flexure in flanges, and case 9, flexure in webs. So all we have to do is determine the value of the width thickness ratio. That is for the flange, that is the B over T, and for the webs we have the H over T sub W. But we need to carefully observe our figure. Alright, so as you can see, so the width to thickness ratio, let's say this is width to thickness ratio is the same as the B over T. So if you are to observe, the value of B is simply half of the width of the flange. So this is the total width of the flange. Let's say that is the B sub. This is the B sub F. So if you are to have its equivalent, so the value of B is simply the B sub F divided by 2, divided by, to be more specific, this is divided by the thickness of the flange. So we can have it as the B sub F divided by twice the thickness of the flange. That will be the width to thickness ratio for flange. Then for the webs, so we have that equivalent as the width to thickness ratio is equal to h divided by, to be more specific, this is the thickness of the web. So what is the value of h? If we are to observe or zoom in on this figure, okay, so the dimension h is, I think this is the end of the fillet of the connection of the flange and the web. Okay, this is how we measure the dimension h. So this dimension from extreme fiber of the flange to this end of fillet of the end of the fillet of the connection of the flange and the web is denoted as k. So we have 1k below and the other k on top. So how do we compute for the value of h? So we have one figure here. So this is the value of k. So this is the starting point on how we measure or how we have the dimension h. So if this is k on the top, another k below, how do we compute for h? So basically we have the value of h is the total depth of the section divided by twice of k, then divided by the thickness of the web. So these are the equivalents of the width to thickness ratio for both flanges and webs. So we have here our limits. So limiting width, thickness, and ratios. So we have the lambda sub p for compact, lambda sub r for non-compact. If we are to simplify, okay, so let's say this is for the flange and for the web, and their corresponding, let's say, corresponding width to thickness ratio. So our limits, we have we have that as the lambda sub p and the lambda, we have the lambda sub r. So if the value of the width to thickness ratio for the flange and the web, let's say this is the width to thickness ratio. If the value of the width to thickness ratio is less than the lambda sub p, so this flange and web are compact. But for the case, for example, that we have the lambda sub p for example, we have the lambda sub p is less than the width to thickness ratio, but less than the lambda sub r. So we categorize these sections as non-compact. And for the last case, let's say, if we have the width to thickness ratio is greater than the lambda sub r, so we categorize these sections as slender. Okay, so that's how we categorize, or how do we know if a section has a compact flange or a compact web. Okay, so again, this is on page 5-44 and 5-45. Specifically, again, if you are to use I-shaped sections, that includes wide flange sections, that will be case 1 and case number 9. Okay, so let's have an example. Okay, so let's have an example. So is the laterally braced section shown below sufficiently strong to support the given loads if Fy is equal to 50 KSI? So if we say laterally braced sections, for problem solving purposes, we can assume that the unbraced length is equal to 0. So that makes, if we say the unbraced length is equal to 0, that makes L sub B is automatically less than L sub P. Then this is under zone 1. As we have the section as W21 by 44, the dead load is 15.23 kilonewtons per meter, and the live load is equal to 43.77 kilonewtons per meter. So we have our Fy. This is Fy is equal to 50 kips per square inch. So we are to multiply this one to the 6.895 mega pascals. And this will now be equal to, so 50 times 6.895. And then, so we round this up to the nearest whole number. So let's say 345 mega pascals. Then for our loading, so for the ultimate uniformly distributed load, so we are to analyze this beam using, let's say, LRFD. As we have the W sub U, the ultimate uniform load is equal to 1.2 of the dead load plus 1.6 of the live loads. So we have W sub U is equal to 1.2 of the 15.23 kilonewtons per meter plus that is 1.6 of 43.77. So W sub U is now equal to 1.2 of 15.23. Then plus the 1.6 of 43.77. So let's say this is 88.308. This is now in terms of the kilonewtons per meter. Then we can now compute for the ultimate moment. This is we have M sub U is equal to the uniform load, the length squared divided by 8. Since we have a beam simply supported, then uniformly distributed loadings. So this is now equal to the 88.308, then multiplied by the length of the beam is 6.4 squared, then divided by 8. So let's have the value of M sub U equal to multiplied by 6.4 squared, then divided by 8. Let's say this is 452.14. So 452.14 kilonewton meter. Okay, now so let us check the properties of a W21 by 44 if it is compact. Okay, just to check the properties of W21 by 44 if it is compact. So let's have the properties in millimeters. So we have its area. Okay, we have the depth is 526 millimeters and the width of the flange is 165. Alright, so thickness of the web is 8.89 and thickness of the flange is 11.4. Okay, the plastic section modulus is 1560. This is times 10 raised to 3 millimeters cube. The value of K is equal to so let's have it as 24.1 millimeters. So let's have the width to thickness ratio of the flange and the web. Okay, so for the flange, so this is the flange width divided by twice the thickness of the flange. So we have that as we have 165, then to be divided by twice of the thickness of the flange, 11.4, and this is equal to we have 165 divided by twice of 11.4, and that is equal to 7.23 or 24. Let's say this is 7.24. Then for the web, this is the h divided by the thickness of the web, or the same as, or we can have it as so this is h over the thickness of the web, or the same as the d, or the total depth of the beam, minus twice the value of K divided by the thickness of the web. And this is now equal to the depth of the beam is 526, or the wide flange, 526 minus twice of the value of K is 24.1, then divided by the thickness of the web, we have 8.89, and this is now equal to so this is 526 minus 2 times 24.1, then divided by 8.89. So we have that as 53.75. So let's say 53.75. Then we are to compare these values to the value of one of our limit, that is the value of the lambda sub p. So what is the value of the lambda sub p for flange? Okay, the value of the lambda sub p for flange is 0.38, the square root of e divided by fy. Okay, so this is, we have 0.38 of the square root of the modulus of elasticity divided by fy. And this is equal to 0.38. The square root of E for steel is 200,000 megapascals. Okay, the value of our fy of the given section is, again, that is 50 ksi, or 345 megapascal. So this is to be divided by 345. So we have this value so equal to 0.38 of 200,000, then divided by 345. That is equal to, let's say we have 9.15. So this is 9.15. If we are now to compare, the value of the lambda sub p, 9.15, is greater than the width to thickness ratio for the flange. So this is 9.15. So therefore, we can conclude that the flange is compact. Okay, it is a compact flange. Okay, well, what is the value of the lambda sub p for the web? Okay, the value of the lambda sub p for the web is that is 3.76, the square root of E divided by fy. Okay, so this is the 3.76. Okay, the square root of E divided by Fy. So this is the same as 3.76, the square root of 200,000 divided by 345 megapascals. And this value is equal to, so let us just edit this one. So here place 0.38 with 3.76. Okay, that is 90. We have 90.53. So again, if we are to observe, the value of the width thickness ratio is less than this, the value of lambda sub p, which is, again, that value is 90.53. So therefore, we can now conclude that both flange and web are compact. So if they are compact, then we can now proceed for the computation of our nominal moment capacity of the section W21 by 44. Okay, so since both flange and web are compact, the section can be analyzed under section 506.2. And since our unbraced length is less than or equal to L sub P, so we can use these equations in computing our nominal moment capacity. So we have okay. So our equation under 506.2 for the computation of the nominal moment capacity for compact sections M sub n, or the M sub P, is equal to F sub y multiplied by the Z sub x. So we have these values as we have Fy is 345 megapascals, or the newtons per square mm. Then multiplied by the plastic section modulus with respect to the x-axis, we have that as 1,560. This is times 10 raised to 3 millimeters raised to 3. That is for a section W21 by 44. If we are to do unit analysis, obviously this is in terms of Newton mm. So we are to multiply 1 kilonewton is to 1,000 newtons. Then we have 1 meter is to 1,000 millimeters. For our answer to be in kilonewton a meter. So this is 345 multiplied by 1,560 times 10 raised to 3. Then to be divided by 1,000 squared. So we have that as 538.2 kilonewton a meter. So again, since this analysis is under LRFD, so our reduction factor is equal to 0.90. So we have the factored nominal moment capacity times the reduction factor. This is M sub n, or P M sub n is equal to 0.90, then multiplied by 538.2 kilonewton a meter. And this is now equal to the ultimate capacity of our section, the W21 by 44. So multiplied by 0.9, and this is 484.38 kilonewton meter. So 484.38 kilonewton meter. So 484.38 kilonewton meter. So what is the ultimate value of our loading, M sub U? That is 452.14. So this is obviously the capacity of our section is greater than 452.14 kilonewton meter. Therefore, we can now answer the question: is the W21 by 44 strong enough to support the given load? Yes, so we can say that the W21 by 44 is adequate when it comes to Okay, the bending moment capacity. So this will be our answer. Okay, W21 by 44 is adequate. Okay, this is our solution for this example.